Good evening. My name's Stephen Peats and I'm Chair of Home Counties South East. And just before I introduce our presenter this evening, I have just a few announcements to make. First of all, thank you for taking the time to attend this evening, and thanks to Laura from Regions Executive at Balham providing all the much needed technical support for this meeting to go ahead. And just really a reminder that CIBSE regions are in place to support the charitable objectives of the institution, encourage intellectual welfare of members and improve the standard of building services engineering among not only our profession, but society in general. And that's carried out by organising periodic meetings, seminars and CPDs as we're presenting tonight, other activities related to the theme of the built environment. So if you have ideas for future meetings or other activities, please put them in the chat box and we'll organise that in the coming year. So a couple of housekeeping points. You could have your cameras turned off and your audio on mute. This will help transmission. And if you have questions, please put them in the chat box. And at the end of the presentation, I will read the questions to the speaker and ask the speaker to respond. So tonight's seminar is on hydronic closed loop system water, and our presenter is Darren Wilkinson, who's the Managing Director of VEXO International. So thank you, Darren, for agreeing to present to us this evening. Over to you.
Thank you for having me, and thank you to everybody for joining this evening. In your own personal time. Okay, so yeah, just very quickly a bit about me. Managing Director at VEXO. Started my career originally in the marine engineering world in the Royal Navy many years ago, and subsequently somehow got into water treatment when I came out of the Navy many years ago. So that's that. But straight into this into the presentation then, the CPD. We're going to be talking over three different modules essentially. The first one is types of closed loop systems that are relevant to the CPD. It's really important because there are different ways to tackle water treatment, water quality, depending on the type of system. We're going to look at, in the other modules as well, we'll look at design considerations that are very important if you want to have a clean and well-commissioned system for the rest of its life, cradle to grave. And then module 3 is really just taking us through kind of competence or competency. It's always a bit of a bandwidth, long bandwidth on that piece in terms of what is competent, but certainly direct you to guides and industries and so on. So that's really what we're going to run through. So to kick things off, types of closed circuit systems. This is relevant to your chiller systems, your condenser systems, and your heating, typical heating, central heating / LPHW water in a commercial building. You could even say the same applies ultimately in the domestic dwelling. What we're not going to be covering really is, and take no notice within this CPD, applying to medium pressure hot water or steam raising plant. So what is a hydronic closed loop system without making you suck too many eggs? A circulatory pressurized heat transfer pipework loop that does not normally require regular makeup. So it's essentially a sealed system. It doesn't have to just be a heating necessarily. You could find this in industrial if you're working on projects in industrial and you have some form of heat transfer. You've got a pressurized loop heat transfer system. The materials generally are made up of various mixed metals, rubber, plastics and fiber washers. No system is really the same. Heating and cooling source can vary, particularly now as we're moving to net zero. But typically you can lose, around about or up to 10% of the system volume over the course of a year, regardless that it's a sealed system. Some can lose much more. So there's plenty of age systems out there at universities and hospitals that lose a lot more water. We were working with a client that was losing 30 ton of water a day at one point. And it's when you have these water losses or this makeup of water, you bring in more problems, unless you, of course, are doing something about it. So I always say, if you take a heating system, without sounding too dramatic, but think of it as a chemical reactor. So we've got different types of metals, we've got water and electrolyte, we've got oxygen, and particularly in a heating system, as we heat water up, chemical reaction rates increase. So I always sort of say, to get the picture in the head, think of it as a chemical reactor. So we need to consider that thermal transfer fluid, that water that we're pushing and pumping around, as it were. What are we going to do about it without, so we don't have that impact in the actual overall system due to poor water quality. So in terms of the objectives of water treatment, sorry, actually, I just realised I should have said something else there. That's a heating system as a chemical reactor. So a chill water system, consider it an incubator. So running at much lower temperatures, we're going to see more issues associated with bacteria and certainly, bacteria-induced corrosion. So both types of systems, heating or cooling, need to be considered. So the objective really is to make sure we maintain the system in a clean condition. So when we design systems, we design for efficiency more so now than ever. We want to be able to assist the maintenance of that system and that efficiency. And we want to prolong the system life as much as we can. When we look at CapEx budgets, particularly, embodied carbon, and we're doing calculations now, digital twins of buildings, understanding cradle to grave. Well, actually, if we don't take care of that water quality, that lifeblood within the system, that's going to throw those calculations out. And overall as well, particularly at project level and trying to hand over, we want to avoid conflict and misunderstanding. So lots can go wrong if we don't get it right, and that generally manifests as things breaking down much sooner than they should do. Your energy bills are scooting up. Again, it's not as per the model. You can have a huge amount of operational issues, customers falling out, and so on. So there's various lists there, but certainly as well, if you do get leaks, you're looking at building fabric damage as well. And unfortunately, litigation, which is quite common, believe it or not, due to poor water quality. So the objectives of the water treatment specification, when you specify water treatment, water quality, typically it's easy to do a cut and paste, and a lot of people I know refer to the BSRA guides. So depending on the size of the system, it comes at a cost, but if you're quoting the BSRA guides, generally, you won't fall short if the contractor is working to the standards. And there's a lot of good information in the BSRA guide in terms of the types of, forms of contract, your method statements, the considerations there, various quality assurance, making sure as well there's plenty of due diligence prior to the project starting. Always good to involve a water treatment specialist at the design stage, because they can come in and advise you on the design in terms of allowances for getting the system clean. Essentially, if you don't have that, it's going to be very challenging thereafter once the system's handed over, if you've not actually fully cleaned and removed any foreign objects or construction deposits or corrosion, etc. So first of all, it's about setting out the roadmap of how you want to deliver your project, and considering, have you got all of that in place in terms and pertaining to water treatment. In terms of basics of the problems we get, keeping it simple, scale, if we're in a hard water area, we see corrosion occurring in our nice new equipment. We can see microbiological growth, sometimes looks like a slime or a slimy sludge that comes from the system. And then we can have fouling and sludge, which is generally composition of all the above. We can also have sometimes systems whereby things are deliberately put into those systems, whether it be, and it's happened, ping pong balls, cans of Coke, nuts and bolts. I even came across a site where there was a hard hat, pair of boots and overalls in a huge condenser strainer. So you never know what you can find. So having the design with the right sort of flushing loops and requirements for the cleaning specialist are really key. And this is kind of what it looks like if it goes wrong. And I say if it goes wrong, there is actually one photograph there that is actually a good photograph, believe it or not, to see, and that's the top left one. In the top left is a system that has had good flushing bypasses, fan cores are all bypassed, and the contractor got those velocities to BSRA standards around the system and removed all of that corrosion debris, and pulled it out of the strainer, as you can see there. So that much heavier detritus was managed to be moved and out of the system. So again, if we don't have the right design, we're not going to remove that. And then what does that mean? In the long term, we're going to be looking at, unfortunately, the other photographs that you're looking at. So whether it's reducing the flow rate, affecting the delta T, complete blockaging of pipe work, plate heat exchangers, and plate heat exchangers, I might add, where we're seeing huge amount of HRU units now installed, or a lot of retrofit involves, typically you see a lot of design with plate heat exchangers to protect the new equipment from, say, for example, an old school heating system. But it doesn't help the client, the building owner, if that secondary side of the plate heat exchanger becomes fouled. They're not going to be getting the heat delivered that they need, and particularly as we move to much zero carbon technologies. To keep in perspective, I always like to say it's a bit like a car. If you've got a car, we understand if we don't change the oil as we should, we don't get it serviced as we should, it's simply we're not going to get the miles or the life cycle out the engine, and we're probably not going to get the miles per gallon from the vehicle either. So it's a bit like that with our heating systems. We design for efficiency, but if we have dirty, filthy water running around your system, you've not taken care of it, chemically and microbiologically, you're going to fall into problems. So we mentioned, or I mentioned, should I say, the various, grenade example, one starting with scale. So scale in hard water areas, it's a mineral that is in solution. It comes through from when we have rain through the bedrock, it picks up these minerals, and ultimately it ends up in our water that comes through our taps. So if we have no pre-treatment prior to going into the closed system, and we're in a hard water area, we are going to introduce scale. Now, ironically, scale can actually act as a bit of an inhibitor. It sort of somewhat passivates, but unfortunately, it opens up other problems. One is obviously energy loss, because we start getting scale buildup on the point of heat exchange, particularly, but that scale will break off, powder off almost, and microscopically it will be very abrasive to the pipework runs and the other bits of equipment that are on the system. So we can either control it through ion exchange, i.e. water softeners, or we can add an inhibitor. So an inhibitor will prevent that scale from precipitating out of solution under temperature. So depending on where you are, where the project is, more to that matter, whether it's in the UK or in the Republic of Ireland, depending on your project, you'll take a look at that, and you should consider, do we need any kind of pre-treatment for this system? Should we have leaks? Should nobody be adding any kind of inhibitor, or there is no pre-treatment at all? It's just something to be aware of. So that's scale. And then we have corrosion. Now, corrosion, very broad term really, but there are various types of corrosion. But a point to note is we can't stop corrosion. If someone says, oh, we can stop it, you can't stop corrosion. It can only be slowed and controlled. So the more we can do to keep the system clean, chemically stable, free from bacteria, we're going to certainly look to hit that 25-year plus that we should expect from the system. Unfortunately, now price in the market, new technologies, pipework systems, some of them are a lot less forgiving than much of the older, much thicker steel systems that were installed 50 years ago, where some systems are still operating. But metal, essentially corrosion, it's the metal wanting to go back to its natural state. So what makes it more corrosive? Well, first of all, it's oxygen. So we want to keep the oxygen out of a closed loop system, which is why you'll see, depending on the system parameters, a dirt and air separator, or a vacuum degasser, or possibly something I'll get onto is the VDI standard, where they use a sacrificial anode. So there are various ways we can manage oxygen, but point being is we want to make sure once that system's filled, we want to get all the oxygen out of the system as best we can. Low pH, so pH running from a number of 1 being very acidic to 14 being very alkaline or caustic. pH neutral is deemed as 7, or it's actually 7.2, but that's kind of in the middle. So there are other things we need to consider. Low pH, so sub, I would say, if I'm honest, sub 7, but certainly less than 6.7. We're going to start seeing increased corrosion rates within the system. So if you've got a lot of corrosion, one of the tests amongst many is pH, the specialist would do. Higher temperatures, again, chemical reactions or corrosion rates and chemical reaction rates increase with temperature. So it's typically why you'll see a lot more of this magnetite in a heating than you would on a chill water system. We can have aggressive ions within the water, for example, chloride. So we can see that can create, stress corrosion cracking, for example, on stainless steel. If it's highly concentrated, certainly locally, we can see failure. And then another corrosive matter we need to consider is debris, sludge, and biofilm. It's like shot blasting inside of the pipework. So if you are using corrosion inhibitor, it'll struggle basically to lay down its film. So you've got to maintain a good level of clean water at the same time and being free of suspended solids. So if we want to control corrosion, we need to basically interfere with the oxygen. That's the first and foremost part, and ultimately be sub 0.2 ppm of oxygen within a system to have control of that. We can try and stop the oxygen getting to the metal, which is where inhibitors can really play their part, or we stop the metal going into solution. That's where your inhibitors or your sacrificial anodes, for that matter, can play their part. So there are things we can do. There are technologies that we can apply. So galvanic corrosion, on the case of corrosion, different types of corrosion. Galvanic corrosion, this is very much when you have dissimilar metals, and the further apart that they are on the galvanic series, you can expect to see a higher rate of chemical reaction taking point at, at that location where the two metals meet. But for it to happen, you need to have water or an electrolyte passing through. So you won't have the same issue if you imagine a flange connection pipe where bolts on the outside, there's no water passing over. It's not such an issue, but it won't be an issue. But certainly on the inside, where we're passing that water through, two different metals meet. So we need to make sure they're not in electrical contact with each other. So it's very much understanding the right types of joints to use, and certainly plenty of PTFE or Teflon tape. But of course, one thing we can't control is if any deposits lay down on the inside of the pipework. Of course, that's a bit like a wiring or imagine a contact being made across a piece of electrical equipment. Suddenly we're going to see localized corrosion taking place. So again, a lot of engineers, when they're designing systems, you typically find the metals, and if you take a look at the galvanic series there, you'll see a lot of the metals are very close together for the most part on that galvanic table. We have something called uniform corrosion. Uniform corrosion is what it says on the tin. It's pretty much, as you see the pipework there on the top right picture, a lot of the surface there is what we would call uniform corrosion. And that's quite easy to predict and to check using corrosion coupons. There are methods as well that we can test that remotely, technologies that are out there as well. And then there's aluminium corrosion. So a huge amount of commercial boilers that are specified. And I know we are moving to heat pump, and we should be moving to heat pumps or other technologies, certainly. But again, aluminium is a great metal in terms of, in terms of ability to transfer energy, transfer heat most efficiently. Unfortunately, in a water treatment situation or water quality situation, aluminium is very sensitive to pH in particular. And a lot of common corrosion inhibitors by water treatment companies that are used are generally alkaline based. And aluminium requires neutral pH treatment. It needs to be maintained below 8.5. Anything over that, we're going to start seeing degradation of the actual aluminium. And you can see boiler failures typically as well, quite common. So we need to try and reduce the oxygen, and that will help reduce the corrosion rate. So there is a correlation between dissolved oxygen and what we'd call free air. And quite frankly, the difference is if you imagine Henry's law, which is if you had a fizzy 2 litre bottle of carbonated fizzy drink, within the bottle there's a pressure, a standing pressure, which is above atmospheric inside that bottle. So that pushes a lot of any gases that are in solution. You can't see them until, of course, you unscrew the lid, and then you start to equalize to atmospheric. We reduce the pressure inside, and those dissolved gases come out, and we can eject them. Obviously, in a closed loop system, not so straightforward. So the only way to do that is either through pressure step degassing, where we actually put it through a volume in a cylinder, a volume of water at a time, and we reduce the temperature. Sorry, we reduce the pressure in that vessel in a moment in time, which reduces dissolved gases that we can then send that water back in the system. But that does take time. You're only doing so much, but over a long period. Heating systems, if I'm honest, you probably find a lot of that oxygen to be used up with the temperature in any case by the time the degasser is looking to do any work. But I certainly see the benefits on chill water systems in particular, and cooling water systems highly valuable, I would say, because the other way that we remove dissolved gases is through temperature. As I said, if temperature increases, they naturally want to come out, and they'll come into sort of that free air state, and they'll come out of an automatic air vent. So there is a correlation. If you remove more of the free air, you will pull out some, not all, but some of the dissolved oxygen as well. Pitting and under deposit corrosion can be very similar in terms of how they look, but pitting corrosion is if you have a dirty pipe work, you're laying down inhibitor and you've got inconsistent film. You have this, if you like, demarcation, I guess, where between one side is anodic and the other's cathodic, because one side is being protected by inhibitor, the other side is not. And unfortunately, that's where we start seeing localized pitting corrosion on the surface. At the same time, we have under deposit corrosion. So as you can see in the bottom left picture, deposits settle out in a low flow area, or as the flow rates encourage things to settle out, like you see there on the radiator. And what happens is we have below the deposits, we have a lot less free oxygen available, and above the deposits there's a higher level of oxygen, and so that creates an electrochemical reaction that drives corrosion locally underneath, hence under deposit corrosion. So again, it's important that we don't, from the get-go, we do not have any deposits that would like to settle out in the system. So we've got to keep the system, again, chemically treated if required, or certainly chemically balanced, and prevent any suspended solids really from circulating. Some bacteria, particularly anaerobic bacteria, sulfate reducing bacteria, they can quite easily thrive underneath those deposits, and as part of their byproduct, even iron bacteria, part of their byproduct, they will actually produce acids, and those acids can then cause pinholing. So if you have horizontal pipe work and you start seeing pinholing, chances are you've had deposits laid down, and it's generally flow rate related. We have crevice corrosion. So again, it's this sort of relationship between the amount of oxygen in one location to the other. If we have a crevice, it's a bit of a dead leg, for example, we're going to see again a drive in the chemical reaction at that location. So the photograph to my left, or to your left, as you look at it, there's a flange, and you can see the damage that's occurred there. And it would appear that really when the flange was bolted together, it wasn't bolted together opposingly when you're tightening up the nuts, a bit like putting a car tire on. Otherwise you won't get a nice firm flush seal, and you allow for this crevice to occur. And the photograph on the right is actually some thin wall press fit carbon steel pipe work, which I see nothing wrong with the, if I'm honest, the installation. I think the installer's butted it up nicely, crimped it nicely, but unfortunately there's a gap, there's a crevice, and so thin wall pipe work is quite unforgiving if you don't get your water quality right, well, particularly carbon steel. Another form of corrosion is erosion corrosion. So if the flow rates are too high, I know it sounds like you're asking for the dreamboat here. They can't be too low, and they can't be too high. Got to be just right, like the Three Bears story. But you do have to have your flow rates right. If you do not, like I say, you'll encourage deposition, but at the same time, if you have too much, you could start looking at erosion corrosion as well, particularly on the softer metals. So the picture on the top left is some copper. You can see that scouring that's occurred. Particularly as well, erosion corrosion, if you've got deposits, once again, it's like shot blasting. You're going to have pump seals failing. So it's normally the first giveaway. If you're getting pump seal leaks, chances are you've got a water quality issue rather than a pump seal issue. Generally, pump manufacturers don't make bad pump seals. So, and then cavitation is another form of corrosion. So rapid formation or collapse of vapor bubbles at a change in fluid pressure adjacent to the actual metal surface. So we can see this, typically, pump impellers, for example, if maybe they're not quite balanced correctly, or the flow rate or the demand into the pump isn't being met. You can hear this, typically you can hear cavitation as well, pumps in particular, this kind of rattling, like they've got bag of nails that are rattling around inside, and that can be extremely damaging. So that is another form. And then there's stress corrosion cracking. Doesn't come up as often as amongst the other issues of corrosion, but typically in our industry, you'd see it mostly on chill water systems. Rather like the fire triangle, to have a fire, you need to have, a fuel source, you need to have heat, and you need to have oxygen. And if you take one of those away, you won't have a fire. Stress corrosion cracking is rather similar. You need a tensile stress. So we've got a hydraulic, closed loop system under pressure. We've got connections that have been threaded and, under pressure where those joints have been made. We need a susceptible material. So in the case of a chill water system, it will be, say, chill water typically. You may have had a bacterial issue, and as a byproduct, they create ammonia. And unfortunately, that ammonia becomes part of the corrosive environment for the system. So the susceptible material in this case would be a brass fitting. Don't see it as often, and certainly see it a lot less than we used to nowadays, because there's DZR brass. But there was a period where engineers would specify bronze on chill water just to be completely, covered, I suppose, rather than a brass. And if you have a poor quality brass, you could have failures. Whereas now, there is the EN standard for brass to be, dezincification resistant. So a much higher quality and a lot less alloys in there, like zinc, for example, that would normally be stripped out by the ammonia, leaving porous copper. I think this is going to start showing its head more so now we move to much lower operating temperatures, but this is another form of corrosion called microbiological influence corrosion, MIC. So essentially we can have bacteria that, if you imagine the fresh water that makes up to the closed loop system, pipework can be sitting there for some time before there's a demand on the system that says only topping up. And in that time, mains water will have very low level of total viable count. It have a low level of bacteria in the water. Typically, we like to think, certainly not any pathogenic concerns, but certainly low levels of bacteria in the water. And of course, if it sits there idle and it's got the right temperature, it's going to proliferate and you're going to have bacteria. So every time the system makes up, you run the risk of giving it a flu almost, you're giving it a dose of this bacteria. Once it's into the system under stagnant conditions, it will multiply. So the bacteria itself will create a biofilm eventually. This slimy looking goo, which you can see on the picture on the right hand side, that's actually a filter, cartridge filter under there. And it's literally the layer of this slime is just peeled off. This was a US military base in upstate New York. They were using a ground source heat pump system or having all kinds of problems. So yeah, and the other thing is they produce, acids and extremely, you get smells as well. You typically know on a cooling system in particular, you get this horrible smell. So that's a concern, localized corrosion because of that, but also indirect will be the breakdown of any inhibitors. Nitrite bacteria. I just noted a typo there actually, embarrassing. Nitrite reducing bacteria, NRBs, are a bacteria that will actually use the inhibitor, the nitrite inhibitor, as a food source. So whilst nitrite is a great inhibitor, it's an alkaline product. So be careful where you use that unless it's a particular blend. It will feed bacteria. Again, giving an anecdotal example, I was walking around a project. I said, how's the water quality? I was told no major issues apart from October. We turn things on. We get a few pump seal failures and a few radiators leaking. So I explained whether that can be avoided. And I said, anything else? He said, oh yeah, we top up loads of nitrite in the as we look to shut down the heating, make sure it's got plenty of inhibitor. But every October we fire it up, it's all gone. So it turns out it was biofilm and bacteria. So in terms of glycol concentration, as we're looking at ground source heat pump systems and other types of renewable systems that will require some level of antifreeze, some level of glycol, we've also got to consider that typically the industry considers anything above 25% volume by volume or dosed glycol antifreeze in a system. It's biostatic. You shouldn't expect to see any issues really. But anything below that, as you can see from this graph, that you start to run the risk that you're going to start feeding the bacteria. So rather than they can't flourish, they actually can flourish as the lower the levels of concentration you go. And unfortunately, not only do they consume your glycol, they actually produce glycolic acid. So you can end up with gassing in the system, acidic pH, and a world of problems essentially. So if you are looking at a system to add glycol, I'd certainly, the industry generally recommends make sure it's at 25%. So module 2. So we've got given you an understanding in terms of corrosion, the types of corrosion and where it can go wrong. So now we need to think about design considerations for a clean and efficient system. And there is quite a lot here from BSRIA that I'm referring to, but I do talk about the VDI a little bit later on. Not as much depth, I'll be completely honest with you. That's still an area that us at VEX are reviewing, including the technologies. We're working with a German manufacturer in that technology as well. But for the moment, BSRIA, let's focusing on BSRIA. So BSRIA is a great tool when you're looking to put something in your specifications to ensure that the contractor is quoting correctly. So but it does talk about the front end, the need for early engagement. And I really do stress that if you can engage with a water treatment specialist early on and say, look, here's my schematics, this is what we're looking to do. These are some of the flow rates we're looking at for the design. Is there anything you'd advise that we should consider? I do recommend that because there's various things about design features, as it says there, permanent or temporary. It may be that there needs to be some valves arranged for a temporary hose to be installed because you're connecting to an existing chiller, and maybe you don't want to leave a hard pipe temporary bypass. So just something, a hard pipe bypass. You want to use something temporary. which things need to be bypassed, what types of methods of cleaning are appropriate for the system, and sometimes whether cleaning is important to be successful. You might have a small system and it's all stainless steel pipe work, and it's, do we really need to go through that? So engage early on, certainly with a specialist would be my advice. And then we have the different sort of stages of the clean to consider. So when the system's first filled, generally it's recommended it's filled with treated water, rather than filling with raw water. And you don't want to fill a system and certainly drain it once you've filled it. It actually makes things a lot worse. But typically the approach the water treatment company will take is dynamic flushing. So this is where they would take terminal units, put them into a bypass situation before you even run those pumps. Once you've got those pumps ran and everything's in bypass, they would then look to dynamically flush, which means that they look at the velocity. So they would plug on a manometer and they would check that they're achieving the flow rates across the horizontal branches of the pipework. So anything above or 5 millimeters up to 5 millimeters in size will be moved. And you can hear this on these projects when this is happening. You can hear things dinker, like a tapping sound almost. As a little nut or a washer, in fact, I've come across. You can hear it moving its way around till it ends up in the strainer. So all that construction debris or anything that might have been put in there, any kind of sabotage even, you want to know that, are you going to have a blockage or is that system going to operate? So good flushing is really, really key. Good velocity is so key. Typically biocide washes for systems at risk from bacteria. If you've got terminal units that are being wet tested, or even chillers that are wet tested, it's a really important question to ask the OEM, because if it's been wet tested, and I found a chiller once many years ago that before we opened it to the main system, and this is before we were in the world of making it a regular thing, biocide washing, we found about 4 inches of biofilm inside the chiller where it had been wet tested and sat on a dock somewhere for probably months. But so a biocide is rather like an antibiotic. If you consider that the system could have slime in those terminal units, let's say, and bacteria, flush the system first at velocity, add your biocide, and what typically happens is the contractor will then backwash, forward wash into the coils, get the air out of the coil and leave it then with biocide. Then they close those coils off, go back to bypass mode. And then whilst the rest of the clean's happening, that you've essentially given those units a shot of bacteria, an antibiotic. Then when you think about cleaning any surface outside, so different types of cleaners are available, particularly if you've got steel. They run the cleaning agent then around the system for a period of time. And then finally they need to come and flush that. Need to consider effluent disposal as well, with within the specification. Can you dispose, or do you need to bring off-site bowsers? But once that cleaning agent, the biocide, is flushed from the system, then they would add the inhibitor and a biocide typically, and then bring online each of those fan coils by back flushing at the same time. Any water loss is made up with inhibitor and biocide. So we want to design for water quality, avoid any dead legs, make sure we've got line size flushing bypasses. I've seen systems with 6-inch district network pipework and a 2-inch bypass, and there's absolutely no way we're ever going to move, the contractor's ever going to move anything sitting in that pipework through a 2-inch bypass. You have to have line size bypasses realistically, particularly if somebody's got to bring in temporary pumps. Treatment starts before filling. So again, make sure that, what's the water quality. Typically add a biocide and inhibitor with your first fill. There are much lower, hazardous risk additives that can be added at that stage. Make sure the flow rates do not encourage deposition or erosion. So typically we certainly don't want to be above, we want to be above 0.5 meters per second. And we don't want to be above the CIBSE guide in terms of maximum flow rates per pipe diameter. Make sure we've got the correct pressure vessel. Really important. See many system failures, and then actually it turns out they haven't been, the vessels themselves haven't been sized correctly. And of course, when the system's operating, it starts drawing in oxygen. Strainers and dirt and air separators, typically filtration at 5 micron and with a form of an alarm. So, whether it's one or all of those technologies, having that sort of technology. Strainers catch your bricks, to use a phrase. They will catch the big heavy stuff in the first pass. That you need your strainers. Dirt and air separators catch the kind of little much granular stuff that will drop out very quickly. And then finally you're left with this very fine sand, which is where you need your filtration as well. But you certainly need to know if these things need changing, i.e. an alarm system. If you are using degassers, please make sure, obviously, check with the manufacturer they are correctly sized for your system. volume, else you really won't be achieving much. Dosing pots are recommended on systems below 1500 litres of a way of adding chemicals, unless, of course, you go down the VDI route. Plastic pipework, this was a major problem years ago, not so much now. People have caught onto it, but a lot of plastic pipework was being installed that was not, it didn't have an oxygen barrier. So it wouldn't let water out the pipework, but it would almost breathe. It would let oxygen in. And the Ministry of Defence had a project years ago that they were changing radiators after 3 months, cost millions, because they created this huge chemical reactor. We do recommend dirt pockets at the bottom of risers, so anything heavy, particularly on the pre-com cleaning, you can grab it without it causing damage around the system. Plenty of vents, sampling points, and if you're working on a shell and core, you do have a fit out. Can have a lot of fit outs. Make sure you've got the right fit out bypasses and isolation. So, i.e., if somebody comes onto that floor, tenant, you can isolate the floor, but open the bypass. Make sure there's a bypass installed, and certainly as close to the riser as you can. Think about flushing valves for the installers on the fit outs as well as the main system, and making sure there's metering stations at the various branches to prove the flushing velocities achieved, basically. So lots there, but essentially the message is design the whole program really accordingly. Going back to BSRIA, they do provide information in terms of what you would expect your flushing contractor to achieve in terms of velocity, dependent on pipe size. So again, if you're looking at, as you design systems, you're looking at what is your flow rate you're looking to achieve at design, just take a look and maybe quick look at the BSRIA guide and say, if we wanted to, could we get up to that? Because there are systems that have been ultra low flow almost, that just impossible to clean as well. So again, all of this is available in the BSRIA guide. As well as information in terms of sampling. There is actually a British standard, BS 8593, that provides a lot of information on sampling as well. Just something we managed to get in here, and CIBSE let us have that in there, a bit cheeky, but something that we've launched recently, Vexo, through BSS as a BOSS product, is actually an inline strainer, but it's got a dry pocket magnet. So idea being is anything that would normally pass through the mesh, we can grab it. Certainly anything that'll be attracted to a magnet, which in most cases, not just magnetite, but that magnetite will be covered in some form of a biofilm and maybe some hard scale. So actually, the more we can do to prevent that strainer mesh from blocking, is going to mean greater efficiency on our pumps and not working so hard, and actually less maintenance. And yeah, to be honest, how often do strainers get cleaned as well, I think. So there are technologies like ours or others. There are other magnetic strainers, I should add that, are available out there as well. So there are technologies to consider that can kind of safeguard, let's say. Circulation is so key for systems. I can't stress that enough. Naturally, people would assume, well, hang on, it's it's the summer, or it's spring and summer. We don't need the heating running at the school now. We're just going to turn everything off and it sits idle. But actually, just like a car, you were going to go off traveling for 6 months. You wouldn't want to leave your car on the drive with the battery connected and not moving the car. It's always good to have somebody, maybe a neighbor or somebody you trust. You ask them maybe to run the car around for you. Keep things moving, just like the human body. If we sit for too long, water quality it's hugely impacted, basically, if you allow it just to sit idle. Particularly if you're using inhibitors, they like to have circulation. So BSRIA recommend 1 hour in every 24 hours, circulate that water, actuate valves, keep things moving, don't let things sort of seize up. And you'll certainly increase the opportunity for things to settle as well. Biocides, going back to, as I said, about bacteria, we want to add a biocide to a system typically to deal with the build-up of the biofilm in the first place. So we don't want bacteria to flourish within our system. And obviously, we don't want to lose any of our inhibitor as well. So if your contractor is adding a biocide, like an antibiotic, it's also very important that it gets added with a biodispersant. So a biocide will kill the bacteria, but it's got to get to it. So if it's protected beneath this biofilm, what will happen is, well, nothing will happen, in fact, because the chemical cannot get there to attack this bacteria. So adding it with a biodispersant will break up that jelly-like substance and allow it to then kill the bacteria. So if you are using inhibitors, and again, I'm just leaning more towards the BSRIA approach, We just need to make sure that it's effective. So for it to be effective, we need a clean system so we can get to the full metal surface or surface of the system. And we want it to be free of pipeworks, scale, biofilm, and so on. Otherwise, we're simply not going to get the level of protection. And really importantly, we want to make sure we're maintaining the right level of inhibitor as well. So, I do come across some sites where the water treatment contractor said, "Oh, there's not enough inhibitor in the system," but they hadn't consulted the manufacturer's product data sheets. Different manufacturers will require different dose rates, let's say, or certain chemical composition and items that you're looking to analyze through a test kit. But keeping the right level of inhibitor is really key. If we are using an antifreeze, again, used in shearwater typically, two types of antifreeze. There's monoethylene glycol. This is the poisonous antifreeze. There's actually been cases, even a movie made once about this, where a lady was slowly poisoning her husband and they couldn't work out what was wrong with him, and she kept bringing him soup to bed. And was adding a very small drop of ethylene glycol, so it is very toxic. And then there's monopropylene, which is suitable for food use. We would recommend, now it comes at a cost, but we would always recommend, if you can, go for propylene glycol and specify propylene glycol. In a world where we're getting better with our ESG agenda, we are thinking about the environment a lot more, and so we should. Think of the risks if you specify or allow someone to use ethylene glycol in a, I don't know, for example, a ground source heat pump, array. What if there's a leak? What if the contractor makes a mistake or there's a spillage? That is going to end up in the aquifer. That's our drinking water. So if you are considering how can we be greener of our projects, I do recommend. Comes at a slight extra cost, but it's well worth it. It's much safer overall. This isn't necessarily my field of speciality or specialism, but it's something I wanted to add in there. And I consulted with somebody at Tata Steel about this, and I think the industry is somewhat now finally changing. But excuse me, carbon steel, whether it's hot or cold form application. So, in a nutshell, when you're specifying, the materials the system's designed for, if you are specifying carbon steel, there is a British and an EN standard in terms of its application. So just know that if you are using cold form, which comes much, let's say, more competitively than the hot form, it also carries risks if you don't apply it correctly to the right sorts of systems. So certainly on cold water systems, but even on hot water systems and even on cold water systems, there can be pH issues potentially. So again, if we're looking to model a building, we're obviously basing that on life cycle of equipment that goes in the building. So if we don't specify correctly, we could see failures. And obviously, if we have a failure in a building of main pipe work, then that's going to impact more than just the heating or the heat. But in this case, particularly the heating system, it's going to be all the building fabric damage that goes with that. So ultimately, I'd go for hot form if you're using closed loop heating cooling systems. Pretty much just what I've covered there. And then as I'm just sort of quickly get to the end of module 2, you'll be glad module 3 won't take too long. As we approach the controls philosophy, or as we approach module 2, the end of module 2, control philosophy is also really key. Only about 20% of commercial buildings have BMS. The other 80% typically have fixed logic controllers, manufacturers' controls. Pretty much it's a time clock essentially. So something to consider when you're looking at the controls philosophy for a closed loop system is understanding, again, as I've said, where you have stagnant conditions, for example, keep water moving. So whatever you can do in the controls piece to mitigate bacterial growth, maintain good levels of treatment around the system, consider all of those things there as part of the design philosophy, control philosophy. So yeah, circulation, think about the pressure in the system, think about the incoming water quality, flow rates, treatment of any biocides potentially, or you can use thermal pasteurization sometimes depending on the system. Certainly think about your water sampling on-site and remote. Now there are a lot of emerging technologies. It's good to, in fact, one's been around for a while. As a company that do remote monitoring of corrosion, I think that's really good. Depending on the size of the project, if you can sort of justify it, I think that'd be a huge bonus for your client. Say the building owner ultimately. But yeah, keeping water quality clean, good water quality with the right level of controls. And we've actually, in fact, took some old systems and we've managed to save the client a significant amount of money on gas by using IoT smart devices along with our water quality approach. The other thing to consider is plant upgrades and integration. Unfortunately, some people have an expectation, well, I've just installed this new boiler and I've got all my heat pump, I've got this new equipment, I've added it to the system, but I want a BSRA standard. I want a BSRA standard for this old system. And, that is, if I'm honest, kind of pie in the sky, because it's one thing trying to hit a BSRA standard for new systems, but when you've got an old, it could be 50-year-old system you might be connecting to you won't achieve, or you could do potentially, but I'd say, manage expectations. Trying to maintain water quality in that sort of system would be very, very challenging. So I think you have to have a bit of pragmatism, have how you approach the secondary side. I mean, one thing we promote typically is if you've got an old system, go for a passive non-flush cleanse of that system. So, filtration with non-flush additives, if you can do that. Sometimes old systems just inhibitor. It's not ideal, but it's, again, we don't want a sprinkler system on that secondary side. And this gives you an idea of what we've managed to pull out of systems. This is with our XPOT and just inhibitor. So 1 hour. This was some years ago now. In fact, that's me modeling my hand with a magnet grate there. But that was what we pulled out after 1 hour. And then 12 days later, you can see in the middle just how much had come out of this 50-year-old. It was about a 50-year-old system. And I actually remember anecdotally, there was the people that worked in the store. It used to be a cinema, then it was a Boots. Yeah, they always had trouble in a hard winter getting the place up to temperature. It later transpired that actually the boilers were undersized as well. But by cleaning up that system, we got the air handling coils, the on-off air temperatures were much better. And the staff said it was the first time, they hadn't been cold in the winter. So again, the impact overall on the efficiency of the system, it can be huge. Older systems, again, coming to that, passive long-term clean is more effective for age systems before you upgrade. And when I say that, what I mean is if you know that your client wants you to I don't know, do a plant room refurbishment and you've got to connect to an existing circuit, the best time to make a difference for that customer is actually going to be 3-6 months beforehand. I mean, I've seen systems take a year to get clean when we do a passive non-invasive approach, which is basically using additives to gently remove deposits. You can see the top left picture there. That was coming out of a 25-year-old plus system at a university, and that's magnetite and biofilm you can see on there. Somebody's holding a magnet grate, and the picture to the right was the main primary header in an old school. So you can imagine doing a quick flush a week in, a week, even over a course of a week before you connect your new equipment, even if you're going to put a plate heat exchanger on there to protect that new equipment, what's coming down the line into that nice new plate heat exchanger. It's just something to consider. So we would certainly recommend getting in there early as soon as you can, because at least when the contractor isolates and does the plant room drain down, you've already tackled the existing secondary. Just some examples there of what we can pull out of the system, but also how quickly then you can clean your magnet grate and get your water quality. I mean, you can see there how clear that is. So XPOTs, again, as well as other filters, again, I can't just promote our product. Any filtration ultimately is going to be a benefit to systems that you have. So if you've got old dosing pots, recommend you do retrofit them with some form of a filter. Otherwise, all you've got is an empty vessel. So if you can retrofit that for something that's going to start pulling out these solids, can make a huge significance to your system, to the efficiency. And we're sort of just getting through on module 3 now, coming to a close before Q&A. So obviously there's a lot of information to take in there, but ultimately as engineers, as somebody designing a system, what should you be telling your customers, or how do you safeguard your customers to ensure your project is delivered on time at the right level as well of quality, and knowing that you're going to be able to give the building owner the model that you designed from cradle to grave. So water quality is key. I hope I've sort of made that clear really through the slides I've showed you today. But what I would say is that, rely on the professionals in the field. Different levels of professionals in the field, I would say, but there are places you can go to. So one of the things I'd recommend is that within the specification, any water quality company, any water treatment company that would come into your premises or come into the site to do any water quality, just specify they should be a member of the CSCA. This is the Closed System Control Association. This organization basically audits, rather like Legionella professionals, the practice Legionella mitigation. Typically, it doesn't have to, but typically are members and highly specified. If anyone wants to look after a hospital, for example, chances are a water treatment company are not going to be able to take on any contract without being a member of the Legionella Control Association. Not many people really know about the CSCA, but I would advise take a look at them, have a look at their website. They vet the water treatment companies. So if you've got 3 prices coming in, you want apples for apples, not just, oh, this one's coming much less. The contract will naturally, we'll go for that. I don't know if it's still the same, but many years ago, I found it was very much packaged up with the M&E contractor when it came to the water quality. But at least with the CSCA, you're going to be getting apples for apples, metaphorically speaking, when it comes to quotations. Other things I put in there, specify lead technicians at least have a minimum of 3 years experience and appropriate evidence of training and a CSCS supervisor's card. You want to make sure you're getting bang for your buck, as it were, as somebody coming on site. It's an important, very important job that needs to be conducted. It's got to be done right at the front end. Other areas, we've been working with Loughborough University, supporting a PhD, and we've seen significant savings by cleaning up existing systems. When you consider the amount of energy in a commercial building that's been used, and this is actually, I need to update this, I do apologise, because now there is a CIBSE Guide M that's come out this year. There's been an update to it, but essentially we're using a huge amount of energy in a commercial building associated with heating and the hot water. And so unless you've got direct fire cylinders, even the hot water is coming off your core heating system. So actually, if that water quality is not right, you can be significantly impacting that efficiency of that system, anywhere from, up to, I would say, potentially 20%. You could be losing efficiency because your pumps are working harder, your strainers are getting blocked, so your pumps are ramping up. Your heat exchangers or your boilers are struggling. So people generally, I've seen over the years, turn up the thermostat on the boiler, the temperature stat on the boiler, and so on, to try and push heat around. So there's a huge amount of savings as well that can be done with energy just by having clean systems. But getting back to biofilm, so scale is as a thermal insulator. We get scale on our boiler. It's going to be putting more gas in or more energy in to meet the same level of demand of energy going out. And actually, biofilm is a greater thermal insulator. So having biofilm on our evaporator coils in a chiller, or even the condenser, or even in a boiler and in our radiators, the bacteria biofilm can create significant loss of energy, particularly where we have a lot of HRUs, heat interface units that are being installed. There was a big surge, wasn't there, on the renewable heat incentives and biomass, for example, things like that. There's a huge amount of incentives, so a lot of these systems installed, but certainly a lot of district heating schemes that are being installed now, feeding up to HRU units. You will have errors on the heat meters, so the ESCO, whoever's providing the energy, essentially will be losing money potentially. I mean, we certainly have some thermal losses anyway that is calculated into like a standing charge, but certainly at the meter itself, if you have turbid water, it will throw out the requirement, the accuracy. So if you are looking to select any kind of equipment, but let's say focus on filtration, it's really important to work with work with the OEM or the manufacturer of the equipment you're looking to install, but also just make sure you double check, do your own homework, that you're selecting the right equipment. And I don't mean that, I don't mean that in any sort of demeaning way. But yeah, selecting the right equipment at the right size, at the right operating temperatures to meet the demands of that system. I've come across problematic jobs where, again, pressure vessels weren't sized correctly. There's been pressure step degassing on heating, and the temperature of the system is way hotter than the manufacturer recommends for their equipment. So you start having all these issues, and it can take months before you get to the root cause. BSRIA do recommend, if you are using any kind of filtration for a system, you have some form of an alarm system to ensure that you can change that filter. When that filter needs to be changed. And if something's difficult to maintain, it probably won't get maintained, or if it's out of sight, it's out of mind. So really, really key that understanding any equipment you install for any application, really, if there is a servicing requirement, you really make it, foolproof, that somebody knows they need to come and change. So cradle to grave sampling, BSRIA states the frequency, but I do recommend the British standard really do support where you should sample from. They also support the frequency, and BSRIA help you to interpret what those samples look like. So again, I guess these slides will be available in any case. So when you look at the resourcing or module 3, these are great places that you can go for information. It's just a bit of a pitch on some work we've done in the past where we've seen energy savings within a week, 3.5% on one particular building. And unfortunately, the filter blocked, and then COVID happened. So that whole trial has been running again, actually. So we're waiting for the outcome. And on the right, we're actually working with Dr. Rainer Mayer many years ago, now about 10 years ago, by adding an inhibitor in his system. It took 3 years. He kept dosing every year, and after the third year, he's no longer had any kind of gassing, didn't have to drain the radiators, and even, he felt the difference on the radiators in terms of heat output. So, water treatment it's not snake oil, it's not black magic. It is literally, it's all about chemically managing your system. There's just some slides here. I'm going to have to, just mindful of time, but there's some slides here of some work we've done with Loughborough University. Various analysis were carried out. I mean, we even saw saving or restoring up to 83.5% of the energy use going into a pump. And I have to say, I mean, bear in mind that is in a lab condition, so it's it's under a very much kind of magnified condition. But I think the arbitrary sort of number I would say is you could be losing 19-20% on energy if you've got fouled strainers, poor water quality in your system. So it's always been a difficult one. How much is this going to save me? Like all questions come ultimately, what's the return of investment? But what's the return of investment? You need to ask yourself if the water quality in that system is so poor that the pumps are working harder and you are having failures and pipework is leaking. And I think we can all associate that if we've got poor water quality, we're going to be heading in that direction. So that does have an impact on the in terms of the efficiency of the system. What we also found as well is the relevance of pressure and the amount of sediment that was added to the system as well. So the higher the pressure, what we actually found was we were actually pulling more out of the unit, but it was blocking much quicker, which one would expect. But because in this case we were using the system pump and we only had the one pump, then that's hence the correlation. But typically most systems are operating over a bar in a commercial system. So again, resources, BSRIA, if you're looking for the chemical / filtration, well, I think you should always have filtration regardless, but certainly if you're looking for a chemical approach, which is generally the most common approach in the UK, BSRIA, it's not a standard in the sense of it's a guide, unfortunately. And even in the latest publication, they try to make the point that you do not need to, or you shouldn't be using it contractually, as a standard. It is a guide, and each system and each site can differ, but unfortunately it's still very much, people are held to that number. That's what it says in the BSRIA guide. You need to hit this level of iron needs to be below this much, therefore you've got to flush the whole system again. And it's just not necessary, really. I think providing that you can prove, you don't want something too far off the BSRIA guides, but providing you can prove that in terms of scientific trends, corrosion is under control, microbes are under control, you're winning essentially. But a great place to go. Closed System Control Association, as I say, they pretty much, if you recognise that them and you put them in to say, you know, in a spec, we want a water treatment company specialist must be a member of CSCA, kind of takes away the whole BISRA stuff, because that's what they should be doing. And then really good guide here. It's not a huge book to get through, but BS 8552, 2012, cradle to grave in terms of sampling, where you should sample. So based on system volume, how many samples do we need to take? I said I would touch on the German VDI. So it works if it's professionally planned and a constructed system. So going back to what I was saying is, if you're looking to deploy the VDI standard and avoid use of chemicals, which I think is a great idea, if we can do that, then yeah, we should certainly do that. But you need to make sure that right at the very front end, you know, you are designing that system appropriately, because it relies on you know, you don't have any ingress of oxygen at all. I mean, it can handle it, but it will impact the equipment ultimately if you have too much of a water loss. But the German VDI, because it doesn't rely on chemistry, adding chemicals, it relies on essentially removing oxygen from the water. If you remove the oxygen, you don't have corrosion. And what makes water more corrosive? Well, obviously oxygen does, but also something actually, the conductivity of the water can make water more corrosive. So naturally, if we had, imagine, you know, demineralized water, very low conductivity, we start adding our chemicals, we'll see the conductivity start to increase. However, we've got inhibitors in there that mitigate any kind of risk of corrosion because of the conductivity. But with the VDI standard, they take the oxygen out. You remove the mineral content, not all of it. We don't want completely, totally removed, because otherwise we'll end up with leaching of like brass fittings, etc. So it's normally about 100 or less, 50 to 100 microsiemens. I recall when it's the VDI standard, and they use a sacrificial anode. So there has a magnesium sacrificial anode that's used within this cylinder, that will sort of, if you like, take the hit rather than the pipe work. You know, it's a bit like they do on ships. It's quite, I say new. I think it's been here probably 5-6 years. We're starting to see more. We've seen it come across. It's starting to prove more popular. Vexo are actually investigating with a German manufacturer something, working on something for us as well, because we don't want to say no to customers. We don't want to say no, we can't offer you an alternative. And Vexo are a green company. You know, we pride ourselves on being green. So if there is something that we feel comfortable with, and we've done our field tests as well, then absolutely we'll join in and offer our clients that, depending on their application and what they need. But that is the non-chemical treatment approach. The only the only downside to that you have to consider is the ongoing. So you don't want a dosing pot, for example, really, if you can have a VDI standard approach, because the minute you add chemicals into a system that is using the VDI, it throws the whole thing out. You know, it's going to cause issues. Oh no, last slide. So yeah, that's me. So I'm happy to take any questions you may have. Thank you.
Thank you, Darren. That was excellent and really informative. Thanks very much. And in fact, I think you've answered a first of the couple of questions. One was from Terry: VDI 2035 and BG50, should they be treated as a comparable document? And then I've got a comment from Ben, who kind of answers that by saying, I think BG50 is based around chemical dosing and filtration, while VDI 2035 is based around chemical-free treatment.
Yeah, absolutely. So they're totally two different approaches. And I think that's the educational piece. Whichever system you go with, you need to be sure that you don't add chemicals in a system that's chemical-free, because it has an impact.
Yeah. And Ben then adds to that comment, I think XPOT is fantastic, but doesn't create the water quality specified in VDI 2035, which I think is increasingly being viewed as the preferred water quality standard, although maybe not fully recognised in the UK yet.
Absolutely. So I think, you know, filtration on its own, whether it's it will aid, whether it's VDI or whether it's chemical treatment. So going back to existing systems, the minute if you've had have a 50-year-old system, it's got no treatment in there at all, but the water quality is clear to look at, it's probably because obviously all that oxygen was used up in the process of corrosion and it settled out. And certainly if you've not had too many leaks thereafter, the minute you add some form of an inhibitor, you're going to start to lift that and you're going to grab it, you'll get increased efficiency and performance. But same with the VDI. If you're looking to approach the VDI on an older system or even on a newer system, VDI it may control the corrosion. That's what it's doing. It's controlling corrosion. But if nothing's ever perfect. If you have any kind of deposit in that water that accrues or is developed anywhere in the system, whether it be a dead lead, what's going to happen? It's going to circulate around that system. So that won't control erosion, corrosion, for example, through those particles. So a good form of filtration on any system is certainly recommended, but you want to avoid encouraging people that, let's say you put an expot on a VDI system. My advice would be take off the funnel, cap it, and make sure there's plenty of signage around that plant room area that any water treatment company, because they've always done it this way, it's quite clear. Do not put chemicals in our system. You will be liable.
Exactly. Question from Douglas. In what form does the automatic monitoring system you mentioned take?
Okay. So typically it's made up of various sensors, dissolved oxygen, pH, pressure, sometimes flow rate, but certainly conductivity, and then a galvanic corrosion sensor. So you'll have these various sort of sensors, and you can get a turbidity test sensor as well, which is suspended solids essentially. And you can, they can be connected remotely and accessed on a cloud platform. So there's a company called Heavershaw. They have some products available. I think they were the first really to bring it to market. I think there was another one I've seen recently, which is a company working with one of the VDI manufacturers. So again, great idea. If OEMs are coming together, I think it's a great idea. So yeah, there are products available. Obviously, they do come at a cost, but it depends on the equipment. If it's a small little heating system versus a district heating system, I think a district heating system or a much larger assets would make sense to have that. It's early warning indicator.
Yeah, brilliant. Question from Richard. Hi, Darren. Thank you for a very interesting presentation. What method of sterilization do you prefer for system makeup water, i.e. pressurization unit feed water?
So some manufacturers will add biocides each time it makes up. UV filtration can be a form of sterilization as well, or potentially, sort of, I'm guessing the Americans would say spitballing here, but you could even have a holding tank that you pasteurize, every so often, and then it pulls from there. You just think of different ways where you could kill or mitigate the bacteria that would be coming in.
Thank you. Question from Tom. What are the differences, advantages and disadvantages of systems like the expot and a side stream filtration unit?
I guess the expot and side stream filtration are essentially one of the same. So both are installed in side stream, or they can be operated on without shutting the system down. I guess pros and cons versus, say, just to understand the question correctly, because they're essentially the same. They're more or less the same. I guess the pros are you're going to capture the much finer particles, that would normally be liberated around the system. The cons really come from, moreover, if it's not maintained. So it's really important, again, that you have some sort of alarm system that, so that would be the cons, because that could then start causing you an issue, adding to your problems potentially as well. Or people think, oh, I've got a side stream filter, and they walk through the plant room and they don't do anything about it. They just know it's there. No one's checking the water quality. So you've got to be holistic in the approach to any system.
Well, I think that's it in terms of questions, Darren. And again, like to thank you for a very informative, excellent presentation.
Thank you.
Very much appreciated by those who attended. Just to let everyone know that this recording is available on the CIBSE website. Darren's going to send me a copy of his presentation, which again we'll put on the CIBSE Home County Southeast page, where you can all download. So it just leaves me to say thank you for everyone who attended tonight, and again, thanks, Darren. Excellent presentation.
Thank you. Enjoy your evening, everybody.
Yeah, you enjoy yours. Thanks again. Bye-bye.
Cheers. Bye-bye.